हेलो स्टूडेंट्स, कैसे हैं आप सभी। सो दिस इज नरेंद्र कुमार द्विवेदी वेलकमिंग यू ऑल once again in the next lecture. So today's first topic, proof of Gauss's law for surface of any shape. हमने पिछले लेक्चर में देखा गॉसेस लॉ का जो प्रूफ था दैट वाज फॉर स्फेरिकली सिमेट्रिक सरफेस. नाउ इट्स नॉट ऑलवेज दैट वी आर गिवन the surface of uniform shape, symmetrical shape. Many of the times the surface given in the problem will be of non-uniform shape. So in that case, how do we apply Gauss's law? How do we prove this Gauss's law? So let's begin with this. So here consider the surface S enclosing charge Q, small q. Now consider surface element ds on this S surface, which is r distance apart, at which the electric field intensity is directed normal to the surface, vector E. Let unit vector be r cap taken along the direction of electric field intensity. Now the area vector of this small surface element will be normal to this surface, and let that area now makes an angle theta with this electric field intensity E. Let this be n cap. And suppose the angle subtended at charge at the position of charge Q due to this surface element V, say d omega, this one. So here the electric flux linked with this surface element is given as the electric flux associated with the surface element ds is, how do we write that? Integral over the whole surface S E dot ds, that has to be equal to integral over closed boundary S E dot. Now for this ds, what can we write here? It is r cap dot n cap into ds. Now see, this electric field has got its magnitude E, and along that direction of electric field intensity, unit vector r cap. So this is electric field intensity. Now area vector ds has been expressed along with its magnitude and direction. So electric flux associated with the surface element, it would be better not to write element, because this is the total flux associated with the whole surface. Associated with the surface S is this thing. Now hereafter we can write integral over the whole closed boundary S E into, now this magnitude of this 1, magnitude of this 1 into cosine of the angle between them cos theta into this ds. Now the electric field intensity due to this charge at this distance can be written as 1 upon 4 pi epsilon naught q upon distance square into this cos theta ds Now this q upon 4 pi epsilon naught along with this r square can be taken out of the integration. So don't take this r square, let it be here inside the integration as it is not constant. So we write now q upon 4 pi epsilon naught integral over closed boundary s. It is ds, this one, cos theta upon this r square Now this ds cos theta upon r square is basically the angle subtended by this small surface element at the position of charge q. So that we can write here integral over closed boundary s factor e dot ds now comes out to be q upon 4 pi epsilon naught into this one, this whole thing now turns to be integral over closed boundary s d omega. So this is d omega. Here you can mention as well on the diagram d omega. So when this gets integrated, so this whole term now gives us the value. We have covered this in first lecture of this Gauss's law, second chapter. So there we had 4 pi. This whole integration will give us 4 pi value. So we just place that into q upon 4 pi epsilon naught equal to. So this 4 pi gets cancelled with this 4 pi, giving us the last outcome to be q upon epsilon naught. So this is the Gauss's law. Surface integral of electric field intensity taken over closed boundary S is always equal to 1 upon epsilon naught times the net charge enclosed by the closed Gaussian surface. So this way we can have the proof for any shaped body, closed boundary, the proof of Gauss's law. Let's have the second topic, deduction of Coulomb's law from Gauss's law. So this is our next topic. So here actually in this topic हम Gauss's law की help से Coulomb's law को derive कर रहे होंगे, deduce कर रहे होंगे. Actually, Coulomb's law is more fundamental than Gauss's law because it came earlier. But this time, using this Gauss's law, हमें इस Coulomb's law को derive करना है. So let's begin with. Suppose the charge small plus q is situated here, and let we have a sphere of radius r enclosing this charge q at its center, and suppose this be the radius of this sphere, where at whose center we are having the existence of or presence of plus q charge. Now suppose we consider a small surface element of this sphere as ds. Now the electric field intensity at a point on this surface will be directed radially outward along this E, and the area vector of this small surface element would also be along this ds vector. So here we first write the electric field intensity here, and later on we will be using Gauss's law and calculating the flux. So to begin with, let's write the applying Gauss's law. What can we write now? Integral over closed boundary S, this is S, E vector dot ds vector, which is equals to 1 upon epsilon naught into Q. So this is basically the Gauss's law that we have just now written. Now here what can we do? We can further move on and just let's have this electric field intensity getting calculated using this Gauss's law. So here we can have, since electric field is uniform, constant you may write, at every point on the surface, therefore you can just take out this electric field intensity and they both are along the same direction, so the angle would be 0, so cos of 0 would make 1. So you directly write E integral over closed boundary S of ds, which is equal to 1 upon epsilon naught into Q. Now here when we integrate this ds, we get S, and S is what? Surface area of this sphere. So for that you can write 4 pi r square equal to 1 upon epsilon naught times Q. Now just cross multiplying this, we have 1 upon 4 pi epsilon naught into Q upon r square. So this is the electric field intensity at this point on this small surface element ds due to the presence of plus Q charge at the center of this spherical surface. Now we'll assume the presence of charge Q naught at this point on this surface element ds. अगर वो चार्ज Q naught यहाँ पे रखा हुआ है जो कि r डिस्टेंस अपार्ट होगा इस सोर्स चार्ज से, तो ऑब्वियस है कि इस पे फोर्स लग रहा होगा ड्यू टू द इलेक्ट्रिक फील्ड क्रिएटेड बाय दिस सोर्स चार्ज. तो वो जो फोर्स होगा ड्यू टू द इलेक्ट्रिक फील्ड ऑफ दिस प्लस Q चार्ज ऑन प्लस Q naught, वो अभी लिख रहे होंगे. Let Q naught be placed on ds, then the force due to electric field intensity E is F equal to what it is? Coulomb's force due to the electric field, F equal to Q naught into E. So just placing the value of E to be this one, here we get 1 upon 4 pi epsilon naught, this thing. Now this Q naught into Q upon R square. So this is basically the Coulomb's law. Now in vector form also you can write, here you can multiply r cap taken along this vector f. So with this, this Coulomb's law gets proved. Now let's have numericals. Okay, so let's begin with, so I'm just reading out the first question. A point charge 17.7 microcoulomb is located at the center of a cube of side 0.03 meter. Find the electric flux through each face of the cube. So let me write the given information in the question. Here point charge is given to be 17.7 microcoulomb. So just convert it in coulombs by multiplying 17.7 with 10 powers to minus 6 coulomb, and it is located at the center of a cube of side A. Let me call the side to be A side of cube. It is 0.03 meter, and find the electric flux through each face. flux through each phase has to be calculated. So here we write now the flux through each phase equal to, as you all know, cube has got 6 faces and the total flux associated with that whole cube is 1 upon epsilon naught times q, net charge enclosed. But here we are calculating the flux through each phase, means through a single phase. So just divide that with 6. Dividing the total flux by 6, we get flux through each phase. So here we have 1 by 6 of q by epsilon naught. So this way we can calculate. Now just placing the values here, we have 1 by 6 into, now the charge is 17.7 into 10 powers to minus 6 into, divided by epsilon naught value 8.85 into 10 powers to minus 12. See students, when you solve this, you'll get the answer approximately 3.3 into 10 powers to 5 Newton meter square per Coulomb. So this would be your answer. Okay, so now the second question I'm just reading out. The electric field components due to a charge inside the cube of side 0.1 meter are Ex equal to alpha x, where alpha equals to 500 Newton per Coulomb per meter, Ey equal to 0, Ez equal to 0. Calculate first the flux through the cube and second the charge inside the cube. So first we need to calculate flux of the cube through the cube and the charge also enclosed within the cube. So let me write the given information here. For the second question, we have cube of side 0.1 meter and electric field along x-axis is given to be alpha into x, where alpha has got the value 500 Newton per Coulomb per meter. So this is the given information. And along y-axis electric field has got 0 component, along z-axis electric field has got 0 component, and we need to calculate total flux through the cube as well as charge enclosed within the cube. So this is the question that is demanding. For the first part we need to calculate flux, and for second charge enclosed. So let's have the solution part now. So here let me make the diagram so that we can have better understanding of the question. So here this is the coordinate, these are coordinate axis. Now x axis, y axis and z axis. So from the origin at 0.1 meter distance we have a cube. So let me make the cube first here. Say this is the cube that we are having, and this is the first face of that cube. Now this one, let me complete the cube. So here actually from this it is 0.1 meter, and this has also got the same as it is cube 0.1 meter. Okay, fine. So this is the question. Pictorially we can represent the question as shown in the diagram. Okay, so now we write flux through the left face. I mean this face. This is the left face. Left face. And this is our right face. Right face. So we are calculating now the flux through left face, and for that flux through left face we can write EL, electric field through that left face dot area vector that we can write delta vector S. So this is the flux through left face. Now we can have the angle between these two. As can be seen, electric field is given along positive x-axis and the area of left face would be directed along negative x-axis. So the angle between these two will be 180 degree. So here we can have the electric field intensity, this alpha into x. So here we can have alpha into A into this, for this area of this left face of cube will be a square one and side is given to be this one. So the side square, A square is the area. Now the angle between them, so that would be cos 180 and here we can write minus of alpha into A cube. So this is our flux through left face. Similarly, you can write the flux through right face. So now the flux through right face of the cube, ER vector dot delta S vector. So on right face, electric field is also directed along positive x and the area vector would also be along the same positive x direction. So the angle between these two will be 0. So here we write alpha A into this thing alpha A, this x has got from this origin we calculate this plus this A plus A. So we write here it to be 2A into this A square side square into this cos 0. So we now reach at 2 alpha A cube. So this is the flux through right face. Now to calculate the net flux, because see only these two faces will have contribution because electric field on y and z are given to be 0. So we are only having these left and right faces which are perpendicular to this x-axis. That means their area vector will be either parallel to x-axis or anti-parallel to x-axis. So here the net or resultant flux phi equals to pi L plus pi R. So just place the values now. Minus alpha A cube plus 2 alpha A cube. So we get only alpha A cube. Now we have alpha value with us and A is also given to us. So just place the values now. It is 500 into 0.1 cube. 0.1 cube. So this, when you solve it, you'll get 0.5 Newton meter square per Coulomb. So this would be your final answer. The first answer that question is asking total flux associated with the surface. Now using Gauss's law we can calculate the second part of the question and for the second part we can write since Q equals to epsilon naught into phi. So this is according to Gauss's law. So here just place the value of absolute permittivity 8.85 into 10 power to minus 12 into 0.5, the value of phi as we calculated for the first part. Now when you just solve it, you get approximately 4.425 into 10 power to minus 12 Coulomb. So this is the answer for the second part of the question. Okay students, so let's have third question now. The electric field in a region is given by vector E equal to E naught x upon L I cap. Find the charge contained inside a cubical volume bounded by the surfaces x equal to 0, x equal to a, y equal to 0, y equal to a, z equal to 0, z equal to a, take E naught equal to 5 into 10 powers to 3 Newton per Coulomb, L length equal to 2 centimeter and A equal to 1 centimeter. Okay, so let's write given information in the question. Electric field vector E is given to be E naught into x upon small l I cap. That is, electric field is being taken along positive x-axis. Now, the cubical volume bounds this electric field and surfaces are bounded by x equal to 0, x equal to a, y equal to 0, y equal to a, and z equal to 0, z equal to a. So this is the volume of cube bounded by these coordinates. Now here we must have another information given in the question. Take E naught to be given to be 5 into 10 powers to 3 Newton per Coulomb. L is given to be 2 centimeter and A is given to be 1 centimeter. So these are the given information in the question. Now question is demanding from us charge contained in the cubical box we need to calculate. Okay, so let's begin the solution part of this question. Now here I'm just drawing these coordinates. So here actually suppose this here actually we are having H, E, A, F, here it is G, let me just draw here this one, G, and here it is D, and here it will be C. These are edges point. Now at this point we have coordinate A 0 0. Now here at this face we have coordinates to be 0 A 0, and one more thing, area vector will be directed along this for this surface. Now here actually the electric field will be directed along this and the area would be along this. So this point let we call here B, and coordinates would be 0 0 A. Okay, so this is a very simple general pictorial representation of these coordinates, volume and faces. So here electric field as is found to be directed along positive x-axis. So rest all faces will have area vector normal to the electric field direction except this face. So the flux would only be associated with this face of cube. So let's begin with flux through face E F G H. So here we write phi equals to electric field intensity. So electric field intensity is given to be E naught x upon L, as this I cap and area vector would be along the same. So that cos 0 along with this magnitude of I cap. So that makes 1. we directly write here. Now area is side square of this face of cube. So just now place the values of E naught is as 5 into 10 power to 3, and x given to be here actually a. This is the value of x upon L is given to be 2 into 10 power to minus 2. Now this further actually into this a square. So this a square will make a cube. So here you can have 5 into 10 power to 3 into 0.01 as the value of this in cube upon 2 into 10 power to minus 2. So this on solving will give us approximately 2.5 into 10 power to minus 1. So this is actually the value of flux that is associated with this cube, where the electric field is given to be this. Now the question is demanding from us charge enclosed. So just for the second part of this question, Q equal to, you can write epsilon naught into phi. So epsilon naught is 8.85 into 10 power to minus 12 into phi is 2.5 into 10 power to minus 1. So students, when you just solve it, you'll get approximately the value 2.2125 into 10 power to minus 12. So this much Coulomb charge will be enclosed by that. So volume of Q. Okay. So the last question is, a spherical volume contains a uniformly distributed charge of density 2 into 10 power to minus 4 Coulomb per cubic meter. Find the electric field at a point inside the volume at a distance 4 centimeter from the center. Okay, so given information in the question, spherical volume contains uniformly distributed charge density. Charge density is given. Actually, volume charge density is given here, 2 into 10 power to minus 4 Coulomb per cubic meter. Okay, now what else? Find the electric field intensity inside the, electric field intensity is to be calculated and distance is given to be 4 centimeter from the center of the spherical volume. Okay, so now let's begin directly. According to Gauss's law, we can write integral over closed surface, spherical surface E dot ds, which is equal to Q by epsilon naught. Now, here actually Q will be written in terms of this surface charge density, volume charge density. So volume charge density, we can write 4 rho into volume, 4 upon 3 pi r cube. So this is actually not. Now it is 2 into 10 power to minus 4 into this 4 upon 3 into this 22 by 7 into r cube upon this epsilon naught 8.854 into 10 power to minus 12. Now since this electric field will be uniform over the whole spherical surface and the area would be 4 pi r square into this E. So here you can just have simplification by cancelling this 4 along with this pi. 4 pi will get cancelled and this r square r will get cancelled. So just on simply E equals to 2 into 10 power to minus 4 into this 3 goes to the denominator part of this 2 into this r is given to be 4 into 10 power to minus 2 in meter divided by 8.85 into 10 power to minus 12. So students, when you solve it, you'll be getting approximately 3 into 10 power to 5 Newton per Coulomb as your answer. So with this, this is the last question that we have covered So I hope you have enjoyed. So do like and subscribe the channel.